All right, section 3 is all about factors affecting solubility. So there's this term called solvation, and it's the process of surrounding solute particles with solvent particles to form a solution. So basically, I think of it as you add salt and the water like attacks it from all sides and pulls it apart.
And you got little sodium ions and
that
then
how
the
you think of
chlorine
it?
ions
That's how I
floating
think of
around.
it.
I look like a dinosaur. It's nothing to do with it.
Okay, so solvation is basically you're surrounding the solute and you're pulling it apart so that you can make it
So it's breaking the ionic bond.
soluble. Yes. And in water, this is called hydration.
Okay.
I'll pause, let you fill in your notes. Okay. All right. Now, likes are going to dissolve likes. So
Okay.
if you have a solute and it has polar properties or it has positive and negative charges, then it's going to be soluble in a polar solvent because they're like each other. And then your non-polar solutes, they are going to be insoluble in a polar solvent.
Okay.
Because they're not alike. So look at your polar solute. It is soluble in polar solvents, insoluble in non-polar. So polar solvent would be something like water.
Okay.
Non-polar, give me an example. Kerosene.
Ew.
Gasoline.
Okay.
Soaps.
Ooh.
Okay. And ionic, again, soluble in polar, insoluble in non-polar. Solutes are non-polar. They're going to be insoluble in polar, soluble in non-polar. Fill in your chart. It's really easy. I think you only have 3 to fill in. All right. Now, you can increase solvation 3 ways.
Oh, you already know how to do this.
Yeah, you do. But you're going to stir it or shake it or agitate it. So think of oil and vinegar. You want to mix those 2 things together. You got to shake it really vigorously to get it all mixed together. And then it's going to go apart in a couple seconds. But then the second one you can do is increase the surface area. So if you have a big solute, break it up into small pieces. It will dissolve faster. So think of granulated sugar versus a big cube of sugar.
Ooh, iced tea.
So if you put a cube of sugar in, it's going to take a long time for it to get very sweet, but granulated sugar will dissolve much faster. Temperature. Solids are going to dissolve faster at high temperatures. So again, think of sugar in hot tea versus iced tea. If you try to add sugar to iced tea, a lot of times you just end up with a whole bunch of sugar at the bottom.
Okay.
And hot tea, it's going to be mixed in. Same with honey. You're going to get the same kinds of things. Gases are going to dissolve better at lower temperatures. So if you think of warm soda, it's normally flat because as you increase the temperature, the gases are going to increase in kinetic energy and they're going to escape faster.
Huh.
So they are not as soluble at high temperatures, but they are at low temperatures.
You're a genius.
All right, solubility is expressed as X grams of solute divided by 100 grams of water.
Okay.
Okay, so we've got 3 different terms here. Unsaturated. This means you have less dissolved solute than a saturated solution. And now you can add more solutes. Saturated is going to have the maximum amount of dissolved solute. And then once you hit that saturation point, anything you add after that is going to make a supersaturated solution. So supersaturated contains more than the max amount of solute. It is pretty much what the word says. And you're going to see solids settling at the bottom. You can also have supersaturated solutions that everything is still in solution. But if you add a seed crystal or you add one more piece of solid, it will start to crystallize in the whole thing.
Ooh, cool.
So unsaturated, saturated, supersaturated. Let's look at that graph that's in your notes. Solubility curve. So if you look at all of these.
That's a lot of stuff.
Oh, yeah. We've got a ton of things on there. In the top left, we've got potassium iodide. Then we've got sodium nitrate. Then we've got potassium nitrate.
Well, let's not go through them all.
We've got them all.
What's on our chart? What's our X and Y?
Okay, your X is going to be your temperature. So this is how much can dissolve at certain temperatures.
All right.
And also you've got your solubility. So your grams of solute divided by your 100 grams of water.
Okay.
So if you follow your line, like say you're following sodium nitrate.
Okay.
Okay. On the line is going to show the saturation point of the solution. So let's just say
Perfect
of.
level.
Yes. So that's the maximum amount that you have. Now, if you go above the line, now you're going to be supersaturated. If
Okay.
you go below the line, then you are unsaturated. So let's say that we are going to add 110 grams of sodium nitrate, and it's going to be at 40 degrees. We're going to end up right here. So do we have a supersaturated or an unsaturated or saturated solution?
Supersaturated because we're above the line.
It's supersaturated. Let's say that we added 110 grams, but now we're at 90 degrees.
Ooh, unsaturated.
There you go. Okay, so that's basically how you read the curve.
Okay.
Okay, we have examples here. So you got to use your graph, your solubility curve. Even though it's not on the screen, you have it in your notes, so look at it. If you have 50 grams of potassium nitrate and it's dissolved in 75 grams of water at 25 degrees, would it be unsaturated, saturated, or supersaturated? So notice that solubility is normally 100 grams of water, not 75.
So we got to change it.
Yep. So we got to do
50
a ratio
divided by 75.
Yes. Okay, so you're going to do 50 grams of KNO3 divided by 75 grams of water. And I would say it's equal to
X over 100, because that's what's on our chart.
yes.
All right, so we're going to cross multiply and divide 50 times 100 divided by 75, and we're going to get 66. Yeah.
Grams of KNO3.
Yep.
Okay, look at your graph. Okay, you've got,
Close enough. 67, but oh
all
well.
right, well,
Okay, so looking at my graph,
you've got 67.
I got to find my KNO3.
Okay, what temperature? 25?
Yeah.
Okay, so we are about here. Your KNO3 is this line here. So, are you saturated, supersaturated, or unsaturated?
Supersaturated because we are above the line.
Very good.
Thanks! Do I get a gold star?
Maybe.
Cookie?
Ooh, maybe. All right, super saturated. What? Am I spelling it right? Yes, A-T-E-D. That's a long word. Okay, so let's do another one where you're going to look at your graph, but in a slightly different way.
Okay.
You've got a saturated solution of potassium nitrate. It's prepared at 60 degrees Celsius using 100 milliliters of water.
Okay.
Now, we know from before that 1 gram equals 1 milliliter. So
Okay.
if you see 100 milliliters, it's really saying 100 grams.
All right.
Okay, how many grams of solute will precipitate out of a solution if the temperature is cooled to 30 degrees C? So it doesn't give you anything about concentrations. However, it does tell you that it's saturated.
Okay.
So we
can
are going to
follow
look
along.
at our graph. So
All right.
find the KNO3 line.
Got it.
Look at 60 degrees.
I'm going to go up. Okay. I think it's a little different than this one.
Yes.
60 degrees up. I'm going to have 100 and,
So 8.
yeah, 108 grams
Okay.
of KNO3.
All right. And that is at 60 degrees.
All right. What are we dropping
C.
it to?
We're dropping down to 30 degrees. So follow along your line.
Drop.
Find 30 degrees Celsius.
All right. I'm going to say it's 48 degrees.
Okay. 48 grams.
Oh, yeah. 48 grams
Okay. 48 grams of KNO3
at 30 degrees.
at 30 degrees. So basically all I did was set up a subtraction problem.
Okay.
So 108 grams minus 48 grams,
60.
we're going to have 60 grams precipitate out. So that means if you cool it from 60 degrees, which in Celsius is pretty hot, and you cool it down to 30 degrees, now all of a sudden you're going to have 60 grams of solid at the bottom.
Okay, because it just can't hold it. It's too cool.
Yep.
Whoa. All right. I'm going to do a little dance to get our light back on. We're back.
We're here. All right. So
Keep going.
use your solubility curve to help you. All right, let's talk about solubility of gases. So there's a few things here. As your temperature of a solution increases, the solubility of gases decrease. We've already kind of talked about this because as you raise the temperature, kinetic energy is increasing, and the gas particles, they already have higher kinetic energy than the liquid, so they're going to escape, get higher, and escape faster.
Okay.
Okay.
Makes sense.
So as the temperature goes up,
Yeah.
the solubility goes down.
Okay.
But if you increase the external pressure, the solubility of the gas increases. So pressure increases, solubility increases. So when bottling carbonated beverages, carbon dioxide gas is dissolved at a pressure higher than your atmospheric pressure, and then they seal it. Okay? And then when you open it, now you're going to have pressure decreasing because the carbon dioxide can now be released and the gas can escape. Therefore, you lose your bubbles, you lose your fizz,
Unless you're opening it, it goes up your nose.
and it goes flat. Now, let's talk about Henry's law. Henry's law deals with the solubility and the pressure.
Okay.
So, at a given temperature, the solubility, S, capital
Okay.
S, of a gas in a liquid is directly proportional to the pressure, capital P, of the gas above the liquid. So, talking about your soda can, the pressure above the liquid is the P that we're talking about, and the solubility is within the liquid, how much gas is dissolved in there.
Okay.
So S1 divided by P1 equals S2 divided by P2. And as the pressure goes up, the solubility is going to go up.
All right.
Write down Henry's law.
Okay.
Let's use it.
Yeah.
If you have 0.85 grams of gas at 4 atmospheres of pressure, it dissolves in 1 liter of water at 25 degrees. How much will dissolve in 1 liter of water at 1 atm?
Things we need to know. Solubility's label is gram per liter. Since we've got grams and the liter in the problem, we're actually good to go, but we're going to have to divide to get our label in that gram per liter. So if they had, say, the 0.85 grams per 2 liters, we would actually have to divide that 0.85 divided by 2 to put that in as our first solubility.
Right.
So just pay attention to what the liters. A lot of times they might just give you the label 0.85 gram/liter and you're good to go. You don't have to do anything extra.
Okay, so I'm labeling it now. You've got S1 is 0.85, pressure 1 is 4 atmospheres.
Do we need to know the temperature?
No?
Nope, it's not involved in Henry's law. We've got S1 over P1, nothing to do with temperature.
Mm-mm.
All right, so we've got to go to what? Our 1 liter is still going to be the same volume, so we don't really need that, but our pressure is going to change. We're dropping from 4 to 1. So we set up X over 1.
Cool.
So we've got 0.85 times 1 divided by 4, and we're going to get a pressure of 0.21 gram per liter.
Solubility.
Sorry, solubility of gram per liter.
2.1
Don't be dyslexic like me. Don't do it.
grams per liter. That equals your solubility.
Solubility, not pressure.
And it is your solubility at 1 atmosphere.
Okay.
So notice it went down,
Yes.
okay, because you went from a high pressure to a lower pressure. And so as your pressure goes down, your solubility is going to go down.
Okay.
They're directly proportional.
All right.
All right, that is all for 14.
Yay!
Enjoy.